recording, so we'll not record the office hours because I think there's no point. But now the recording is live, and so let me remind you what we did last week, and then there's a few things left in week 1 that I want to finish, and then we'll move over to week 2. So week 1, last time we ended with this theorem, and this theorem helps us to determine whether a subset of a vector space is actually a subspace. And the difference is that a subset can be anything, any collection of objects, but a vector is a subspace, has to satisfy certain properties. And there's a list of them, but this is actually bolted down to fewer of them, so that's easy to check. And so now the question is, which of these listed here is actually subspace? Have you had a chance to look at these already, or should I give you 2 minutes to go through them? I'll just give you 1 to 2 minutes, and then whenever someone has an idea, just raise your hand and just tell me if you want to tell me if you want to say something about a specific number here. Oliver, you have your hand up. Is that already a question, or?
Yeah, I propose that question. I mean, number 1 is a vector space, and since well, first of all, since it's continuous, we know it will be injective and surjective, and we know that all functions f in all real numbers are their own vector space as well, and they follow the rules with axioms which are underlined in the vector space. And it was
so let me interrupt you there for a second, because you said that they are injective and surjective. Continuity doesn't imply anything of that. So continuity means that I should probably start a new page. So about 1. So f as the function from R to R is continuous. Wait, is that how I spell continuous? No, it's not. It's continuous if for all x in R, the limit of we call this x0 of x towards x0 of f of x is equal to f of x0. So this is what it means. I guess we could also talk about surjective functions, and then yeah, I mean, since you proposed it, I guess we could say 1b surjective functions of R to R in all functions f R R, and in this case it would not be a subspace because it doesn't contain the 0. So this would be an easy way to say that 1b is not a subspace. So this implies that, what do I call this? Maybe just search, F search, RR. This is not standard notation, so don't quote me on this. but this has no zero vector. Okay, any questions about this? So I kind of skipped the first one, but the second one is just as well. It's just as good of an example. Let's do one or two more of these. Can some of you maybe just pick one and tell me what do you think about these? Andrew, can you tell me what you think?
So I was thinking that the plane the line as defined by number 3 isn't a subspace, as it doesn't contain the origin.
Yes. So there's many ways in we can solve this. And I mean, you kind of, I don't know if you wanted to do this geometrically or algebraically, but so let me just do this algebraically. So the zero vector in R2 the zero vector in R2 does not lie, or is not in, did I give this a name? The set simply because 0 plus 0 is equal to 0 and not 1. So it doesn't satisfy the condition. And this is the one that we prune out by. Yes, very good. So someone asked if in the chat, how do we know that the zero vector is 0, 0? And in this case, I told you that this is a subspace in R2. So this specifies, I think last time we called this the ambient space, or like this is the vector space in which we will consider the subspace to be in. So the ambient space forces the operations and also the zero. And the way that we define R2, unless we do something obscure and we define the addition differently, and the zero vector is -1, -1, if we don't specify anything absurd, then we think of them as the normal R2. So maybe that wasn't clear. Also, I just read the chat, but in general, I might not see questions in the chat. So if you have a question like this, I would encourage you to actually raise your hand, because then I can stop and answer it. Okay, let's pick as the last one something that is actually subspace, so that we don't have. Let's do number 7. Why not 7? So anyone who has something to say about 7?
Wait, so you're saying 7 is a vector space?
Yes, a subspace, and therefore yes, a vector space too. Do you want to make a guess why? I mean, basically, the solution will be applying the theorem.
Would it be because, well, if you add two even functions, you'll get an even function. Well, they're separate sets, right?
Yeah. So technically, there's two parts, but let's just do the even ones. So just forget about these for now. Yes, the idea is good. So let's write this down. So first of all, just graphically, what does it mean for a function to be even? Well, it just means that whatever is happening on the left-hand side of the the y-axis is also the same on the right-hand side, so that so the value of x and minus x is the same. So f of x and f of minus x is the same value, which is this. And of course, odd would be the opposite in this case. I mean, the sine function is a very famous. This is not the sine function. In this case, if we take an x value and we take minus x, then it would be minus the value. And now, by theorem, what is this the number? 128. I mean that's the number in the book, so that's so you can find it in the book too. Any number that I give theorems is the same as in the book. Otherwise, I don't number theorems and such because I think it will be confusing. We need to check. Andrew, do you have an idea?
Well, I just wanted to say that maybe like the additive identity, namely the zero function, is both an even and an odd function, so it's a member of both sets. So
yes, exactly. So that's a good comment. F of x equals 0 is both even and odd. So that's already, if this wasn't true, then this would be a very quick way to say that one of them is not a subspace, but in this case it's necessary but not sufficient. So this theorem 1.28 says that we have to check two things. First, it's non-empty, and second of all, that alpha v plus w is in the set for any vectors and scalar. So let's start with the first one, with the first thing we need to check. F even RR is non-empty. And this is, I mean, what Andrew just said already solves this because 0, f of x equals 0 is even. It doesn't have to be the identity function. It could be anything. So this is just lucky coincidence. And second of all, pick any real number alpha and two even functions. F of x, g of x. So we only assume that they're even, but nothing else is known. They could be technically anything. Okay, I need another page. And then, so now we want to show alpha times f plus g of x is even. This is what we need to show in order to show that the operation multiplying by a scalar and then adding another vector is preserving, is still in the subset. So let's do this. Well, how do we do this? We just plug in minus x and show if the name is x. So we literally just write alpha times f plus g. And we give it the argument minus x. And now comes the operation into play, because we need to know what is the operation. Well, this is just alpha f of minus x plus g of minus x. So we do, this is pointwise addition. And then similarly here, next step is we do pointwise scalar multiplication. So again, same reason that we can write f of x times alpha. Sorry, of minus x. Okay, and now we use the assumption. So by assumption, g of minus x equals g of x, because we said let f and g be two even functions. And we also have that f of minus x is equal to g. No, this is not true. F of x. Right. So we conclude that this is alpha times f of x plus g of x. And now we just do the pointwise thing backwards, just to have the same expression as in the beginning. So we can write this is alpha times f plus g applied to x. And then we're done, because now we can say, you pick this color. Now we can say that alpha times f plus g is also even. Hence, alpha times f plus g is in this subset in question. Oliver, you have a question.
Yeah, I might have missed it. Why did we just do the minus x at the beginning?
So what does it mean? I mean, the question is this still an element in the set, in the subset, in this VIP lounge of functions? This is like a certain selection. The question is, what is this? What is the selection? And the selection, as you can see here, is given by a condition that these have to be equal. So for any function that I give you and ask you, is this a member of this subset? You have to test if this is true. So we just tested this, and then
that tests it if it's even.
Yes.
Okay. And there's a discussion in the chat about number one, just the first part. People are saying it is a vector space, since you can add continuous. Let's say you can add two continuous functions and it will stay continuous. And
this one, yes.
Yeah.
This one, no.
Okay.
Okay. Thanks for delaying for relaying the question in the chat.
No worries.
Okay. Any other questions? I feel like I talk too much in this discussion. This is not supposed to be just me talking if it's a discussion. But we'll have more discussions today, and then I'll get a chance to work more on this. So we didn't get through all of them, but just look through them if you like. And this is something we could talk in my office hours next week, if you want to go through this more. Okay, so I want to do a quick definition, which actually I just added yesterday, but I thought it was important for later. So if we have two subspaces, then we can take their sum. So this is not a sum of vectors, but it's a sum of subspaces, and this gives us a new set. And the set is simply defined to be any element that can be written as a sum of elements in these subspaces. Does that make sense? Any questions about the definition? I could probably come up with a quick example. So for example, like this is a really quick and easy example. The space of vectors with just non-zero values in the first two entries. So this will be, of course, a vector in yeah, A and B are obviously numbers. This might be written as a sum. This might be written as a sum of just a vector with just the first entry non-zero. And of course, A is in R. And then, of course, we need another subspace, which is just a second entry non-zero. I mean, and this is simply because if you have a vector with 2 non-zero entries, you might as well write them as a sum of this plus this. And then this will be an element in here, and this is an element in here. These are element in symbols, not size, as someone thought last time. So this is just the idea of adding 2 subspaces. We will need this later, and I think this is a good place to mention this. Okay. Well, now comes the time that we need this. So I want to give you some properties. Before we move on to week 2, I want to give you some idea of how you can build new subspaces from old ones. In this case, if you have 2 subspaces, there is a theorem that says the intersection will also be a subspace. And I think I'm going to skip the proof, but the proof is actually not too hard. You can just look into the book and convince yourself. It just boils down to the fact that they're both subspaces, and so the properties of these subspaces apply to the intersection as well. And also the sum u plus w is also a subspace. And you can use theorem 1.28 to actually apply this in a more abstract way. So in the examples that we looked at today, it was quite concrete, but this is more abstract, and it's still the same idea, just in a more abstract sense. Okay, and oh yeah, actually, I actually made an example for you. So in this case, let me define symmetric and antisymmetric matrices. So I'm just going to call this curly S symmetric matrices. And this is a matrix A in MAT2R, such that the transpose of A is equal to A. And if we define the antisymmetric matrices, then it's very similar. It's all the matrices such that the transpose is minus A. Okay, why does this help us? Well, this is an example where if you continue looking at what exactly this means, and with this I actually need to tear this apart. So if you look at this, this is the set of all the elements, all of the 2x2 matrices, and the condition. I mean, what happens if we transpose? We just mirror them along the diagonal. So it will be AD and then CB. And the condition just translates to that these have to be equal. And that just means B and C have to be equal. Same here. So in total, this will be all the matrices A, B, B, D in in all 2x2 matrices. Right, and similarly here, if we have A, B, C, D, and we require that that the transpose, which is still A, D, and C and B switched, is equal to minus A, minus B, minus D, and minus C, you can observe that the diagonal entries have to be 0, because here this means A equals A is only true if A equals 0. Same for D. But C and B are still allowed to be non-zero. We just need B to be minus C. So we will see that this is equal to 0, A minus A and 0. In MAT2R. Okay, let me not talk about this today. We don't have time for this additional topic. Instead, let me just conclude that in this part, you can check that any matrix, let's say M in MAT2R can be written as M equals a symmetric part plus an anti-symmetric part. So how do you do this? Well, observe what happens if you apply. And this is, I won't go through this, but I just claim, and this is a very easy verification that you can do, that M symmetric is just equal to 1/2 M plus M transpose. And M anti-symmetric is equal to 1/2 M minus MT. And you can check that they sum to M again. And so what I've done here is I've written them. I mean, if you verify what I claimed here, I've checked that this decomposition into a symmetric matrix and an anti-symmetric matrix always exists for all matrices. And therefore, the space of matrices of size 2 by 2 can be written as, I wrote symmetric plus anti-symmetric. Yuan, you have a question?
Can you scroll above a bit?
Yes.
So in the last line, why is it A minus A, not AA, if minus B has to be minus C?
Right. So if you look at these conditions here, then we see that C has to be equal to minus B for this equality of matrices to hold.
Oh.
So I think that's the best answer I can give right now. You can also check that this will make it skew symmetric. I mean anti-symmetric. And if you had anything else here, it wouldn't be anti-symmetric. Okay, I think, yeah, I don't want to say anything about this today. We'll say, I'll probably mention this another time. Any questions before we move on to week 2? I'm terrified to look at the time, but it is what it is.
So basically what you just said is that you can take a vector system and make it into 2 subsets, and if you add them, you can get that that subspace, right?
Yes. It doesn't mean that this exists for any kind of vector space, but you can always, I mean, I'm just giving an example of when a vector space has 2 subspaces, and when you sum them together, they give back the whole vector space. So just to explain an example of this, so that that you have an idea of what it means to sum 2 vector spaces, 2 subspaces. All right. So it's about time to get to week 2, and we'll see how far we get, but we'll start with linear independence, and then we'll hopefully get through the rest tomorrow. This is equivalent to section 1.3, and I'll just start right off with the first definition. So when you take a vector space, you may have a subspace, but they're very, very many vectors in there. So what I mean by the family of vectors, this is not supposed to be a subspace eventually. This is just means let's just pick out k vectors and let's just give them a name together. So if you have such a family of vectors, then there's something that we call a linear combination, and it just means that we add them all together with possibly coefficients. So it just means that if you have three vectors, you're allowed to scale them first. This is what the alphas are for, and then you add them together. And vector addition is done by just concatenating them. So in this case, we take the first one scaled, the second one scaled, and the third one scaled. Just some notation. We say that this is trivial if every coefficient is 0. But notice that this means that the linear combination is 0 itself. Because if you have 0 times v1 plus 0 times v2 plus 0, not the 0 vector, just the 0 number, times vk, this is 0. So we just say that this combination is trivial. And this will be important later on. So just for easier communication, we'll need this word. And to abbreviate this sum, well, notice that this sum looks very generic. So we have many summons and they all look the same. This is always an alpha with a vector, an alpha with a vector. They just have labels which are 1 to k. And so when we have this sum, we may abbreviate this by just saying, well, let's have a sum of these terms alpha I vi, where the I starts at 1 and ends at k. So this is just another notation for this thing. And whenever you have this, you can also just write it out. But it might be easier to have this short-term notation because it doesn't take as much space to write. Yuan, your hand is still up, or is that a new question or old one?
No, sorry, I forgot to put it down.
Okay, no problem. Okay, just notice quickly that this way of producing linear combinations encompasses every operation that we know in a vector space. So this is the most arbitrary, the most general way to combine these vectors. And to give you an example, well, if we have monomials, they're also polynomials. It just means that they have only one power of x. Then, well, a linear combination of these literally is, let's just call them v1 and this one v. This is unfortunate, but let's just call this v4. Then we see that, well, if we have alpha times the first vector, actually, no, we don't need the names. Alpha times 1, alpha 0 plus alpha 1 times x, and so on. This will be exactly a polynomial of degree at most 3. So the difference between a normal polynomial and the linear combination are so subtle that it's almost not obvious, not clear why I made this example, I think. So this is just the sum of the alpha I x to the I, and in this case we have started 0 because the first power of x is 0 to 3, and this linear combination happens to be exactly the same as a polynomial. So this is just any plain old polynomial. No, any term can be 0. It doesn't matter if it's a leading term or non-leading term. I mean, even a polynomial of degree 2 is still valid in P3. It just means at most. So it's fine to have one of the terms being completely 0. And even if all the terms are 0, then it's a trivial linear combination, and it's still the 0 vector. Any other questions? No. Oh, sorry, I read your question again. Sorry, I was jumping the lines. Okay, secondly, and this is something that many students find confusing, at least when I was teaching linear algebra. A year ago, it was a different course, but linear algebra. So observe that if we take any vector x, y, z, the generic vector for x, y, z arbitrary, then observe that x, y, z can be written as just the vector with a non-zero x value plus 0, y, 0 plus 0, 0, z. And now observe that we can multiply, we can even further decompose this with x times 1, 0, 0 plus y times 0, 0, 1, 0, 1, 0 plus z times 0, 0, 1. Of course, here x, y, and z are just real numbers. So now notice that this is the linear combination of what we usually call E1, E2, and E3. So if you want to represent any vector in R3, you can just specify a linear combination of these. And funnily enough, the coefficients of these combinations, so let me just write this here, the coefficients of the combination. Don't confuse these axes, x, y, and z with vectors. In this case, they're just numbers. They're same, they're equal to the entries of the vector. And this is not a coincidence. I'll probably explain this in detail, how this happens, and you will observe that this happens in a more general framework. But this is just observation. So for now, that combinations of these three vectors, E1, E2, E3, are exactly all the vectors in R3. Are there any questions? Did I write that there's an S somewhere? I usually denote a set, a family of vectors by S, but I don't think I used S in here. Okay, now let's get to another definition, and then I'll finally let you discuss something in the last 10 minutes. So if you have these kind of families of vectors and you can take linear combinations of them, it is almost obvious to guess that we want to give the set of all possible linear combinations a name. And so this is exactly what this span is. So if we have a family of vectors, v1 to vk, and we consider any possible combination of them. And what I mean by different combinations is just that if the coefficients are different, then it's a different combination. If you add this vector, if you add these vectors together with coefficients 1, then you get this. But if you double this vector first and then add them together, you get a different vector. So the coefficients change the combination. And span S is the set of all possible linear combinations with these vectors and any coefficients. If the set happens to be empty, then we just, by convention, call this, denote this by the vector space just containing the 0. And I mean, as we saw in the previous discussion already, just now with different notation, with a new notation, this is already discussed above, that the span of these monomials actually give you back any kind of polynomial. If you just tweak the coefficients in the combination, that tweaks the coefficients in the polynomial. So now, for maybe 3 minutes, I want to give you time to think about how could we span all possible matrices. So what should I write here in the span? So that if I apply the span, then I get all possible matrices. Okay, I'll give you 3 minutes. I saw that someone already wrote the answer in the chat, or a answer. Let me remind you that you should not give away answers in this chat until everyone had time to think about them. So, I mean, if you have a way to communicate somewhere else, that's fine. If you can set direct messages, if you know each other, then just use direct messaging, or maybe just message some arbitrary student in this chat. Yeah, and you can also type out the answer, and then when it's time to answer, you can just hit send. Okay, who can say something about this? Maybe raise your hand and then just unmute yourself. Yes, Andrew.
So I guess like it could be like 4 elementary matrices, not elementary. I mean like 4 matrices where it's like it contains 1, 1, and 0 everywhere else. So the 1 will be positioned respectively in each of the corners.
Yes, correct. So this is very reminiscent of what we just looked at for R3, and not a surprise because it's just another vector space with vectors that are tuples of some kind. We only write them as a square, not like as a column. Is this the only answer? Are there other different? So what if I give you, for example, this one? Could you complete this to still span this? Let me just leave this open as a question. And I mean, we're going to see this later in this lecture, so I'm not going to. Sam, you had your hand up if you want to say something.
Oh, no, I'm good.
Okay. So yeah, we'll answer this question in a different format for a different vector space later. Okay, so in the last 5 minutes, let me see another discussion. can we? Yes, let's do this theorem first, and then we'll start with the discussion next time. So this theorem, I think we can do in the last 4 minutes. So what this theorem says, and it's very important, it says that for any vector space, if we are given a family of vectors and we take their span, so far we only had this as a subset. So I said this is a set of all linear combinations, but now this theorem says it's even more, it's subspace. And this is a very important theorem because it's not obvious, it's not clear. How can we prove this? There's this we can use theorem 1.28 from last week. And I mean, I'm just going to explain it to you. You can read it in the book too, I guess, if it's proven there. So as introduced before, an arbitrary linear combination and now I'm going to use this shorthand notation because it's going to save me time and space. So I'm going to just write alpha I times vi, where these are just some coefficients, and I runs for the k. And we can also choose a different coefficients, say beta I, but the vectors have to be the same for it to be in the same span of S. And here I also runs from 1 to k. And then we also choose a scalar. Say in this case C in R. So how do we add two linear combinations? I guess that's the only thing that's not clear how to apply 1 to 8. Does anyone have an idea how we could add two linear combinations? As a hint, you can look at polynomials, because polynomials are just linear combinations of very specific spans, or very specific monomials. Adrian.
Yeah, can we just add the coefficients, because we'll have the same vectors anyway, so we can just have like alpha I plus beta I for each
Yes.
vector.
Yes, correct. So we just, let me write so the coefficients that correspond to the same vector, both combinations, will be added together. And then I guess same question, how do we multiply the linear combination by a number C in the reals? Actually, this is not this. You don't have to guess this. I think Andrew just wrote in the chat that we can use the distributive property. So this is given. If someone knows by any chance which axiom this was, I think it's one of the later axioms. Just fill this in here. And this means, I think I'll be done with this in 4 minutes, and then I'll stop the lecture. So because linear combination, the alphas, if we write this out, then we just have alpha 1, v1, and so on. These are just vectors. It doesn't matter if they have coefficients or not. But as Andrew noticed, that we have this property that if you multiply the sum of two vectors or many more vectors, then we can just distribute it over these vectors. So this is C alpha 1, v1, and so on. So they each get their share of C. And now if you write this back in the shorthand notation, we observe that now is this still in a combination or is this not a combination? I mean, how do we interpret this? Oh, you want to say this is axiom 9. Thank you. So now the trick is really just how you perceive this answer, how you view this, how you interpret this. And now the key is view this as a new coefficient, or as a new set, as new coefficients. And then this whole thing is just another combination. It just has different coefficients, but it's still a linear combination. Okay, so let's get to 1.28, the application of this. So to prove this, is a subspace. We need to show two things. Again, the first one is span S is non-empty. And I mean, there are two cases. Either S is non-empty, so then the span of S at least contains S. So whatever is in S will also be in the span S. Or if S is empty, then by convention, we still have the zero vector. Okay, and the second one, the last condition, is we need to check that C times one vector, in this case, a combination VI, plus another combination, and we picked these at the beginning, is still in the subspace, in the subset. But now, if you do this, we first take in the C as we discussed above, just here. I told you how to multiply this. And then we have the sum of two linear combinations, and we just do this coefficient-wise. Meaning now we have a, we get is C alpha I plus beta I VI. And again, the solution is given by viewing this as a new coefficient. Of another linear combination. And so therefore, this is actually, I mean, it's the same vectors. It's the same vectors here, just different coefficients. But that's fine because we just said any coefficients are welcome. And so this is still in span S. Yeah, and then we're done. This is a subspace by theorem 1 to 8. And I will end the lecture right now. I'll probably go over the last steps that we just did. But that was very quickly. So I'll start tomorrow just by going over this thing once more. but I'm also happy to answer questions that you may have right now. But if you need to go, then you're free to go now. Let me stop the recording. And yes, Oliver.
I just have a question, not really related to this, but it's related to linear algebra. Let's say you have you're proving an axiom, and you have this result. Can you add a 0, but on both ends to cancel out the y's?
Sorry, can you repeat? You want to add a 0 to what?
I wrote it in chat. So let's say you're given a result like that. Can you add a 0, but using one of the axioms where 0 is equivalent to y minus its plus its inverse, additive inverse, but instead of adding it at all together, can you add it at the end to cancel out the y's on the end to get x?
Yes. So the second expression you wrote is true. That is equivalent. Let me just. I'll delete this afterwards. I mean, I can just write this temporarily. So if you have x, you may add 0. That's not a problem.
Mm-hmm.
And then 0 can basically undergo mitosis and become any vector with its inverse. So this can always split into two things which are anti of each other, which are the opposites, the inverses.
Mm-hmm.
What you can't do is write x and then have one on the right side and one on the left side. This is not allowed, because this would be basically this step that I did on the top, and also switching around this to the front. So this would involve two steps, and I mean, yeah, in our case, actually, it is valid. So I mean, this is okay to do, but you should be careful to do this in two steps. So this is not just one steps.
If you're this is referring to A1, and if you're not allowed to use commutativity or whatever, I forgot how you pronounce it, but
yeah,
you wouldn't be able to do that because you're using because since you're trying to prove if it's commutative, you can't do it.
Yes, exactly. I think this is referring to the assignment question.
Yes.
Yeah. Yes. So you can't do this in one step. This is only in one step. What you can do is the first line. That's still fine. And then you can go from there wherever you want to go.
Mm-hmm. Does commutativity, or I don't know how you pronounce it, but
I think it's I know it's called commutativity and commutative. It's yeah. I always speak too fast when I say these words, but it's commutative.
It's commutative. Is it only referring when it's two different variables, or is it also a rule when it applies to two of the same variables?
Oh, you mean if you add x plus x, right?
Yeah, and can you flip it?
Yeah, but if you flip it, that you won't even see if you flip it. Like.
Okay, so let's say and negative x would be a different variable then, right?
Yes, negative x is a different
Vector.
Is a different element. So if y is equal to minus x, then x minus x and minus x plus x, this uses commutativity.
Okay.
I hope I didn't give away too much from the solution of the assignment, but
no,
yeah,
I'm still trying to figure it out. But yeah, but thank you.
Okay, you're welcome. Jency, or how do you pronounce your name?
Yeah, that's correct, Jency. Yeah. So I have a question about the set addition you just defined.
the set addition in week 1.
But you defined that today.
Do you mean this?
Yes.
Okay.
Let's say you have two sets, U and W, and you know the supreme of U and supreme of W. Can you make any conclusion about the supreme of U plus W?
The supremum.
The least upper bound.
I'm confused because this is not something that we use ever in linear algebra. So I think this is a different addition of sets, maybe, or so this question does not. I mean, it's not a bad question at all, but I just don't know how to interpret it, and it's not really important for linear algebra. So, and the reason because why I'm just don't know how to answer is mainly because, so to define a supremum, you need to order elements. But I mean, is V less than W? What does that even mean? So so the supremum only makes sense of, say, the set S only makes sense, is only valid if S has a norm. So this means you need to say, what does it mean to have a size in S, and we haven't done anything like that.
Oh.
How did you come up with this question?
Yeah, it's just like, I had like this question for like another course, but then since we defined set addition, so I just asked it.
Oh, I see. Okay. Maybe even the addition of sets is different in that course, because here we adding subspaces, and probably if you take calculus or something where this might be relevant, then addition of sets is not the same.
I see. Thank you.
Okay, you're welcome. Yuan?
I was just wondering if we could go over which axioms you used to define addition and multiplication.
In what? In here?
Yes.
So the addition. I guess the addition also follows from an axiom. If you have alpha 1 v1 plus alpha 2 v2, just as a very short linear combination, and then you add beta 1 v1 plus beta 2 v2. Well, first of all, you use commutativity to bring the v1s together and the v2s. So you would have alpha 1 v1 plus beta 1 v1, and then you would have beta 2 alpha 2 v2 plus beta 2 v2. And at this point, then there's another axiom. So this was commutativity. And then we use distributive property over scalar addition. So then we can factor these two together, and we just get the v1 outside. Yes, so that's a good comment, because this means that that none of these are chosen.
Okay. I was confused why we could quote the axioms if they're just vectors in a set, but also the set. Wait, yeah. Why can we use the axioms if they're not, like, if we don't know that it's a vector space?
Oh, because the vectors in span S are linear combinations in another vector space. So because we have, I guess that's almost like a philosophical question. It's really just about if you write these down, these two combinations, the first one and the second one, and you have a larger sum of vectors with coefficients, then basically the axioms just allow you to boil them down into, again, a shorter sum. And then we just see that this is the right shape of a linear combination.
But the exercise is trying to prove that span of S is a vector. No, we're not trying to prove that. We're trying to prove that it's a subset.
A subspace.
A subspace, which would make it, never mind. Okay.
Okay, I can answer 2 more questions. Quinn Yuan.
Oh, hi. I have a question about last week's lecture. Maybe, I think I'm still confused about functions to be a vector space. That I don't really understand how functions can be vector, and what will be the zero vector for the function?
The zero vector.
Yeah.
Well, this goes back to this slide, I think.
Yeah.
So if you're looking for the meaning, then I can't help you. There's no really meaning behind this. But what I can tell you is that if you consider the set of all functions and you define the addition in the way that we did, which was pointwise addition. So whenever you have the sum of 2 functions,
yeah,
and you apply it to a variable x, then you just apply the functions separately, and you apply addition in the target space. Then it just happens so that this will be this set together with these 2 operations will be a vector space. So you can just go through the axioms and check that these hold.
Yeah, so we're just like dealing with those functions as vectors, and because they can add with each other and with scalar multiplications.
Yeah. If you could add apples together and you could scale apples, then this would maybe be a vector space, but there's no meaning behind this. So it's two different questions. Is it true, or why is it true? And here I only said it's true, but the latter one I can't really answer.
Oh, okay. Oh, so what can we say about the zero vector? Maybe the function.
Oh, the zero vector will be just the constantly zero function. So the function that's everywhere 0, that will be 0, the zero vector.
Oh, I see.
Okay, one more question. I think there was some Z.
Yeah, you can just call me Claire. Yeah.
Claire.
Yeah, I'm confused about the differences between field and subspace. It's like we have field axiom, and we also need something to prove if we want to prove something at the subspace. I'm confused about that, the differences.
So I didn't introduce any field axioms in this lecture so far.
I mean
fields.
I mean the one that you have used, the axiom, like commutative, like that one.
Yes.
Yeah, these one axioms. Yeah, I'm confused about the relationship between these axioms and the one and what we need to prove when we need to prove something is a subspace or space.
Oh, okay. So if you want to prove something is a vector space, as in the previous question, the set of functions, then you need to go through all the 10 axioms. That just, if you start from scratch, then this is what you need to do. However, if you have a vector space given, so you assume that you already have something to start with, and you have a subset, then it's easier to show that it's a subspace compared to showing that it's just a vector space. And this is exactly given by this theorem. So basically, this theorem is a shortcut. Technically, you would have to show all the 10 axioms again for a subspace. Yeah. But you're able to use this theorem as like a magic trick, and then it just reduces.
So 1, 2, 4, and 6. 5 and 6.
Yeah, that was the discussion here, right? Yeah. So only 1, 2, 5, and 6 are left open if you talk about subspaces. But it gets even better because 1, 2, 4, and 1, 2, 5, and 6 are already checked if you only check these two. So in the end, this is only the only thing you need to do. So we've gone from 10 axioms to 4 axioms for subspaces, not all vector spaces, and then just 2 different facts we need to check.
Oh, so this is the one that I need to check if we want to say something in the subspace.
Yes, precisely.
Okay, thank you.
Okay. If there are more questions, I can answer them tomorrow, maybe before the lecture or afterwards. Or if they're longer questions, I'm happy to discuss in my office hours, whatever you have to ask. Okay. Oh, the recording's still going. Oh, geez. Okay. I'll see you tomorrow. Bye, everyone.